So, anybody remember what a rational number was? If it's in decimal form, it repeats or terminates. But how else can it be written? Fractions. Yes. Okay, I guess I'm still writing this back. So when we did rational numbers, we said they were numbers that could be written as a fraction. Something over something. Notice what word is inside the word rational. Fraction or slightly shorter. There's ratio. And how do we write a ratio in math? We write them with something over something, so we write them as fractions. So if you ever see the word rational on anything, you know you are going to be looking at a fraction. Guaranteed. You just did rational exponents less than a month ago. Rational exponents were those lovely little problems you all loved so much when I gave you like x to the 2/3 power. An exponent that was a fraction, that's a rational exponent. And we now all know that, of course, those turn into roots, and so everything is great and happy. So, once again, rational net fraction. So if we're doing rational functions this time, what on earth is a rational function going to be? Well, guess. A fraction, but it's a whole function. So it's a fraction with variables in it. So rational functions are fractions containing variables. Now, we could go for weeks, probably months, on all the different rational functions that are out there. Particularly if we start trying to graph these babies. Because there are a million different things I can put in a fraction. I can put something like that. I can put 1 over x plus 2. I can put x over x minus 3. I can put 4 over x plus 3 times x minus 7. I mean, there's so many different things I can put in a fraction. We could be at it for the rest of our lives trying to figure out all the things there are to know about rational functions. So needless to say, we aren't doing that. When we graph them, I'm only going to ask you to learn 2 basic graphs of them. To graph ones like that, or even more complicated, can be done. It's really not an easy or manageable task until you can use calculus graphing methods on it. So I won't be making you graph multi-term fractions. Not worth the to do it by algebra is tedious nightmare. It would be silly to, I think it would be silly to teach you that. You have a piece of technology that can graph it for you right now. You need to do more with it than that, you wait for calculus. So that's a rational function. So today our goal is very simple. How does one add, subtract, multiply, and divide these fractions that have variables in them? You already know how to add, subtract, multiply, and divide fractions. We just want to do it with variables. The method you use is exactly the same. It's just that you get to use some algebra in the middle of it. So, which is easier, adding and subtracting or multiplying and dividing? Fractions. You should have multiplying and dividing is substantially easier than adding and subtracting. So we're going to do multiplication and division first. I really don't like that color. Okay, I said yesterday's class and the video was awfully noisy. You could make enough noise for them to know that you exist. So, let's check with basic numbers. If I said take 14/15 times 24/35, what would you all do to multiply those fractions? What were you taught was particularly the shortcut to it? Do I need a common denominator to multiply? No. Yeah, you can, but you're not multiplying, you're cross-canceling. You're reducing it. You're cross-canceling, you're not cross-multiplying. But can't you also reduce within the same fraction? Yeah. So actually when you're multiplying, you can cancel any numerator with any denominator. Anything you can cancel from any numerator to any denominator works. Okay, so what could I reduce here? Okay, 14 and 35 would reduce by 7. So that would make this a 2 and that a 5. Okay, what about any other numbers? They reduced by 3, so that would make that a 5 and an 8. Okay, so then how do you multiply it together once you have it reduced? Do you multiply across, like an X, or do you multiply straight across? Yeah, straight across. Do you multiply the denominator, or do I keep it as a 5 since it's a common denominator? You times it, yes. So multiplying straight across would give me 16 over 25. And if you got everything reduced correctly, that shouldn't reduce any farther. Now, it never hurts for you to stop and look at it and go, okay, will it go any farther? Did I miss something? Because occasionally you miss seeing something that would reduce. Well, we're going to do the exact same thing, except we're going to do it with variables. That was probably not good. I didn't pull it completely apart. So let's throw some variables in there and make this have some more pizzazz. So 16ab cubed divided by 25 over the, or 25 times the quantity 4 minus c. Then we have 5 times the quantity c minus 4 and 12a to the 4th b. And just to make it more fun and show that you can do this, you can even multiply by a third fraction at the same time. There is no limit on how many fractions you can multiply by. Okay, remember, you are allowed to cancel any numerator with any denominator. Okay. But because this is going to get really messy as we cancel this, I want to talk about quantities a second. Can I cancel, like, this c and this c? You have to cancel whole quantities, and they have to be exactly the same quantity. Okay, so can I cancel 4 minus c and c minus 4? No. But this is a slick trick you need to learn because you're going to do it a whole bunch of times in this chapter. They're really close, aren't they? Yeah, they just need to switch by a negative. So if you need one of them to switch, you can. It's like you're factoring a negative one. You pull a negative out to the front, and you can change the sign. So like I would prefer this with c minus 4. I'm going to factor a negative out. I'm going to make that negative 25. It'll make the c become positive and the 4 change to a negative. Causes them to reverse, and now I can cancel. So then I can say, hey, goodbye c minus 4s. What else can we adios? Okay, 3 plus 2s. Okay, if we're going to do numbers then, all right. 3 goes into 12 and leaves me 4. All right. Okay, 16 and the 4, is that what you said? Okay, so 4 cancels into 16, which would leave me still with a 4. Ah, yes. Out here even farther, I have this 2 could cancel into that 4, which would then leave me at what? That would leave me at 2 left. Ah, 5 and 25, yes. 5 and 25 would leave me with that negative 5 still there. And then, yes, variables. Got an a with an a to the 4th, which would then become, yeah, that would become a cubed. So this b would make it become a square, but this b would make it become a b to the 1st power. And then the biggest problem is you have this giant mess, and you have to figure out what on earth do I have left. Okay, I would go across. I got a 2, a b to the 1st. Is there anything else left on the top? Nope, so we got a 2b left on top. That cancels to an a to the 3rd, and that's it. And so you cancel all that stuff, and you're down to this nice little simple expression. Pretty sweet, huh? I remember learning to do some of this in Algebra 1 and thinking this is the coolest thing ever, that I could cancel all this stuff off. I just thought it was a great thing. Okay, I'm a math nerd. I'm sorry. It was just really cool that it worked. So, but we have even more fun coming, so don't worry. One thing I might suggest, you might want to leave like a line of space above and below these so that you got room to write all the stuff that's left. Because the biggest mistake I see on these problems is people just can't figure out what they canceled and what's left. They can't find it in the mess. So try to do it in some form of an organized manner. It will help. But you're going, that was too simple, bring it on. Well, what if you noticed hardly any of those had pluses or minuses, or if they did, it was a whole quantity? What happens if I give you something like this, where each term is separated by a plus or a minus? So now, like, can I cancel this top x squared with the x cubed below it? Not when there's minuses and pluses. You can't cancel individual terms with pluses and minuses. You can only cancel whole quantities. At the moment, I do not see any quantities that are exactly the same. So what do I do? Actually, bookers, I did that wrong. I wanted to kill two birds with one stone, and it's not my notes. We're going to kill... because I don't want to have to do a whole nother problem. That was supposed to be this way. Divided by. We needed to talk about division. Which is going to come out to be the exact same thing in a second. Because, how do you divide fractions? The reciprocal of the second one, yes. And then you add, subtract, multiply, or divide them. You multiply them, yeah. So it's actually going to be the same thing in a second. I just forgot to write it as a division problem. So you're actually going to multiply then and flip that second one over. My bottom numbers, oh, whoa, dude. Thank you. X cubed minus 4x squared plus 16x all over 4 minus x. Okay. So it's the same problem I just had there a minute ago, but yeah, if I was you, if I'm copying the problem out of the book and I see it's division, I'd just flip it over right then. No reason to have to write it twice. So, but we always know it's always the second one you flip. Yes? Okay. All right. So now, back to the same problem though. I still can't cancel anything. They're not like entire quantities that are alike. So what algebraic thing do we know how to do that might help us? Factor. You have to factor them all down into factors because then you can cancel factors. But some of these are requiring some factoring rules we learned back in December right before Christmas, and so I'm confident that since we learned it right before Christmas that you guys have this down perfectly. Remember every word I said. So a brief review of our factoring rules, since it's been a while. I taught you if there were two terms, you looked at it and said, do I have perfect squares or cubes? Anybody remember the quick way to factor perfect squares? Yes, there you go. A plus b and a minus b. The ones that are conjugates, that way the middle term cancels when you FOIL it. So, you see squares that are subtracted, that's the easy one. Do you remember what you did to squares that were added? You're remembering cubes. Hang on to that thought. We're going there in a minute. Not factorable? Because can you get the middle term to cancel if that's all pluses? So yeah, that was not factorable. You got squares that are added, it won't go any farther. You're stuck with the two square things that are added. You can't take it any farther. Okay, now, what JC was just about to remember, yes, I taught you a rule for doing things that were cubes. And when you did cubes, it was a binomial, two terms, times a trinomial. Kind of ring a bell? Okay, anybody remember how you got, the binomial was the easy part. You just take your original problem, and without the cubes, it just becomes a minus b. You have to get rid of the cubes, you keep the same sign. It was the trinomial that was the tricky part. You squared whatever you had written here for A. You squared it. Okay, you combined the AB, but what sign did you use? Opposite sign. If that was a minus, you did a plus AB. And then you had to square the last term. But what happens to anything when it's squared? It's positive. So the last one's always positive, because if you square it, it will be a plus. And you were left with that much. And also a reminder, that trinomial will never go any farther. You cannot factor that anymore. It won't work out. So you have to try. You can do a cubed plus b cubed. You have to change two signs. Which two signs? Yeah. The minus at front becomes a plus. So therefore, the middle term gets a minus. The last one's always plus because you're squaring it. It's got to be positive when you square it. Okay, so those are going to show up occasionally, not tons, but you're going to see them some. I think that was two terms. I think you all are experts at three terms. What's the only way to factor a three-term or trinomial? Two binomials, unfoil it, whatever you want to call it. Oh, if you see three terms, that's what you're going to try. Okay, what about four terms? And then somebody said it. Grouping, yes. So the question is, do you remember how to factor by grouping? Let me throw you one, because there's not a four-term up there, so let me throw you a four-term expression here. Oh, that's not a line, sorry. I'm not doing fractions yet. Okay, so four terms, you group what? Yeah. And when you group the first two and the last two, you want to group, when you group the last two, get that sign in there, get that plus in there. That matters, because you have to pull it out. So you go, what's the common factor to the first two terms? You can take x squared out. What's left? If I take x squared out of those two, I'll have x minus 3. Okay. Now, when you do the second two, if that's a plus, then you're pulling out a plus something. In this case, what can I take out? A 2, which will leave me with. Okay. Does it matter if those two quantities are the same? Yeah. They have to be the same. If they're not the same, this doesn't factor, and you are done. They have to be the same. But are you done right there? I have lots of people who quit right there and forget to do the next step. Because now you're going, oh, look, this is a group, this is a group. What's the common factor that's in both of those groups? X minus 3 is in both of those groups, so I'm pulling x minus 3 out front, which means I would have what left? The x squared plus 2 would be left then, because I took x minus 3 out to the front. So you should end up with two binomials if you factor four terms. And you'll see, they'll show up once or twice. Get a little four-term action. Okay, so now that we are experts at factoring, never to be missed again. Oh, shoot. Hold it, stop, we're pausing.